Here's something that will mess with your head. Right now, as you read these words, you might be sitting inside something that has no edge, no boundary, no final frontier. Something that goes on and on and on without ever stopping. Something infinite. But wait, that doesn't make sense, does it? Everything you've ever experienced has limits. Your room has walls. Your city has borders. Even the biggest things you can think of, countries, oceans, planets, they all end somewhere. So how could the universe itself have no end? This isn't just some abstract puzzle that keeps philosophers awake at night. This is a question that strikes at the very heart of reality, and the answer, whatever it turns out to be, will fundamentally change how you see your place in existence. Because if space truly goes on forever, then somewhere out there, impossibly far away, there's another planet exactly like Earth, another you, reading these exact same words. In fact, there are infinitely many versions of you, living infinitely many slightly different lives. The very idea seems to break our brains. How can something have no end? How can space go on forever? And if it does, what does that mean for us, for reality, for everything we think we understand about existence itself? Tonight, we're going to embark on a journey through space and time, through the minds of brilliant scientists and philosophers, through mathematical equations and cosmic observations, to explore this mind-bending question that sits at the very heart of our understanding of reality. But before we dive into the deep end of cosmic infinity, let me share something that might surprise you. The question of whether space is infinite isn't just an abstract philosophical puzzle. It's a question with real, measurable consequences that scientists are actively investigating right now, using some of the most sophisticated instruments ever built. The answer could fundamentally change how we understand not just the universe, but our place within it. So buckle up, because we're about to explore one of the most counterintuitive, brain-melting, and beautiful ideas in all of human knowledge. We're going to discover why infinity isn't just a mathematical concept, but potentially a physical reality that surrounds us every moment of our lives. And along the way, we'll encounter paradoxes that have puzzled the greatest minds in history, discoveries that revolutionized our understanding of space and time, and questions that remain unanswered even today. The story begins, as many great stories do, with ancient humans looking up at the night sky and asking themselves a simple question: where does it all end? Imagine you're an ancient Greek philosopher, perhaps a student walking through the groves near Athens around 500 BCE. The world feels vast, but comprehensible. You can walk to the edge of your city-state, you can sail to the edge of the Mediterranean, you can climb to the top of the highest mountain. Everything you encounter has boundaries, has limits, has edges. But then you look up at the night sky, and suddenly you're confronted with something that seems to stretch beyond all human understanding. This was exactly the kind of question that fascinated philosophers like Anaximander and later Aristotle. But it was a philosopher named Archytas who posed what might be the first version of our infinite space paradox around 400 BCE. Archytas asked a deceptively simple question: if I travel to the edge of the universe and stretch out my hand, can I extend it beyond that edge? If I can, then there must be space beyond what I thought was the edge. But if I can't extend my hand, then something must be blocking it, which means there's something beyond the supposed edge. Either way, the universe can't have a true edge. This argument, elegant in its simplicity, would echo through centuries of philosophical and scientific thought. But Archytas and his contemporaries were working with a very different picture of the universe than we have today. To them, the Earth was the center of everything, surrounded by crystalline spheres carrying the sun, moon, and stars. The idea of infinite space was more of a logical puzzle than a physical reality. Aristotle, whose ideas would dominate Western thought for nearly 2,000 years, was deeply uncomfortable with the idea of infinity. To him, infinity was a concept that led to logical contradictions and philosophical problems. He argued that the universe must be finite, bounded by the outermost sphere of fixed stars. Space, in Aristotle's view, was not empty void, but rather the collection of places occupied by objects. Without objects, there could be no space. This solved the infinity problem by simply denying that empty space could exist. But even as Aristotle's finite universe dominated scholarly thinking, other voices whispered of stranger possibilities. The atomist philosophers like Democritus and Epicurus proposed that beyond our visible world lay an infinite void filled with countless atoms combining and recombining to form countless worlds. These ancient thinkers, working with nothing but pure reasoning, stumbled upon ideas that wouldn't be seriously considered by mainstream science for another 2 millennia. Fast forward to the medieval period, and we find scholars grappling with the theological implications of infinite space. If God is infinite and omnipresent, doesn't that suggest that space itself might be infinite? The Islamic philosopher Al-Ghazali and later Christian thinkers like Henry of Ghent wrestled with these questions, trying to reconcile divine infinity with the Aristotelian finite cosmos. But it was during the Renaissance that our modern understanding of infinite space began to take shape, and it happened in one of the most dramatic and dangerous ways imaginable. In 1584, a former Dominican monk named Giordano Bruno published a work called On the Infinite Universe and Worlds. Bruno took the radical step of extending the Copernican revolution to its logical extreme. If Earth wasn't the center of the universe, and if the sun was just another star, then perhaps the stars themselves were suns with their own planets. And if that was true, then the universe might be infinite, filled with countless worlds like our own. Bruno's ideas were breathtaking in their scope and terrifying in their implications. An infinite universe filled with countless worlds challenged not just scientific orthodoxy, but religious doctrine. The Catholic Church was not amused. Bruno was arrested, tried for heresy, and in 1600 he was burned at the stake in Rome's Campo de' Fiori. His last words, according to witnesses, were defiant. "You may be more afraid to bring that sentence against me than I am to accept it." Bruno died for his vision of infinite space, but his ideas would not die with him. Within decades, the telescope would reveal that the universe was indeed far stranger and more vast than anyone had imagined. Galileo's observations of Jupiter's moons and the phases of Venus confirmed that we lived in a sun-centered system. Later, astronomers would discover that the Milky Way was just one of countless galaxies scattered throughout space. Bruno's infinite universe was becoming scientific reality. But here's where our story takes an unexpected turn. Just as scientists were beginning to accept the possibility of infinite space, mathematics was revealing that infinity itself was far more complicated than anyone had realized. In the late 19th century, a German mathematician named Georg Cantor made a discovery that shook the foundations of mathematical thinking. Cantor proved that there were actually different sizes of infinity. Not all infinities are created equal. The set of whole numbers is infinite, but the set of real numbers is a larger infinity, and there are even larger infinities beyond that, stretching upward in a hierarchy that has no end. Cantor's work revealed that infinity wasn't just a concept meaning very large or without end. Infinity was a precise mathematical object with specific properties and relationships. But Cantor's discoveries came with a price. The deeper he delved into the nature of infinity, the more he encountered paradoxes that seemed to threaten the logical foundations of mathematics itself. Consider, for example, Hilbert's Hotel, a thought experiment proposed by mathematician David Hilbert. Imagine a hotel with infinitely many rooms, all of which are occupied. Now suppose a new guest arrives. Can you accommodate them? In a normal hotel, the answer would be no. But in an infinite hotel, you can simply ask all guests to move from room N to room N plus 1. This frees up room 1 for the new guest. Now suppose infinitely many new guests arrive. Can you accommodate them? Surprisingly, yes. You can ask the guest in room N to move to room 2N, which frees up all the odd-numbered rooms for the new guests. This kind of mathematical manipulation works perfectly in the abstract world of mathematics, but what does it mean for physical reality? If space is truly infinite, do these mathematical properties apply to the physical universe? Can you have infinitely many planets, infinitely many copies of Earth, infinitely many copies of you? These questions bring us to one of the most profound issues in modern cosmology, the difference between mathematical infinity and physical infinity. Mathematics can handle infinite sets with precise rules and operations, but physics deals with measurable, observable reality. Can the universe actually contain infinite quantities of matter and energy? Or are there physical limits that mathematics doesn't capture? This is where our story intersects with one of the most revolutionary discoveries in the history of science, Einstein's theory of relativity. In 1905, Einstein published his special theory of relativity, which revealed that space and time are not the fixed, absolute entities that Newton had imagined. Instead, they form a unified fabric called space-time that can stretch, compress, and warp. Then, in 1915, Einstein completed his general theory of relativity, showing that matter and energy tell space-time how to curve, and curved space-time tells matter how to move. Einstein's equations immediately raised new questions about the nature of space. If space-time could curve and warp, what did that mean for the overall geometry of the universe? Could space be finite but unbounded, like the surface of a sphere, or could it extend infinitely in all directions? Einstein himself initially believed the universe should be static and finite. He was so convinced of this that when his own equations suggested the universe should be either expanding or contracting, he added a cosmological constant to force it to remain static. It was one of the few times in his career that Einstein's physical intuition led him astray. The truth about the universe's expansion came from observations, not theory. In the 1920s, an American astronomer named Edwin Hubble made a discovery that would revolutionize our understanding of cosmic space. Using the powerful 100-inch telescope at Mount Wilson Observatory, Hubble observed that distant galaxies appeared to be moving away from us. More surprisingly, the farther away a galaxy was, the faster it seemed to be receding. Hubble's discovery implied something almost unthinkable. The universe itself was expanding. Space was literally growing, carrying galaxies apart like raisins in a rising loaf of bread. If the universe was expanding now, that meant it must have been smaller in the past. Trace that expansion backward, and you arrive at a moment when all the matter and energy in the universe was concentrated in an infinitely dense point. This was the birth of the Big Bang Theory. But here's where the infinity paradox becomes even more puzzling. If the universe began as a point and has been expanding for a finite time, how can space be infinite? This question has led cosmologists to distinguish between two different aspects of cosmic space: the observable universe and the universe as a whole. The observable universe is the spherical region of space from which light has had time to reach us since the Big Bang. This region has a finite radius of about 46.5 billion light-years, and it contains a finite amount of matter and energy. We can study this observable universe using telescopes and other instruments, and it's clearly finite in size. But the universe as a whole might be much larger than the observable universe, or it might even be infinite. This distinction is crucial for understanding the infinity paradox. When we ask whether space is infinite, we're really asking about the geometry and extent of space-time itself, not just the part we can observe. To understand how space could be infinite, we need to dive into the geometry of the universe. Einstein's equations allow for three basic types of cosmic geometry, each with different implications for infinity. The first possibility is a closed universe, which has positive curvature like the surface of a sphere. In this geometry, space is finite but has no boundary. If you travel far enough in any direction, you'll eventually return to your starting point, just as a ship sailing in a straight line on Earth's surface will eventually circumnavigate the globe. A closed universe contains a finite amount of space and matter. The second possibility is a flat universe, which has zero curvature like an infinite sheet of paper. In this geometry, space extends infinitely in all directions. The angles of triangles add up to exactly 180 degrees, parallel lines never meet, and the universe contains infinite space and potentially infinite matter. The third possibility is an open universe, which has negative curvature like a saddle shape. This geometry also extends infinitely in all directions, but with different geometric properties than flat space. In an open universe, the angles of triangles add up to less than 180 degrees, and parallel lines diverge from each other. So which type of geometry describes our actual universe? This is where modern cosmology becomes detective work on a cosmic scale. The key to determining the universe's geometry lies in measuring its overall density. Einstein's equations tell us that the geometry of space-time is determined by the total amount of matter and energy it contains. If the universe has exactly the critical density, it will be geometrically flat and infinite. If it has more than the critical density, it will be closed and finite. If it has less than the critical density, it will be open and infinite. For decades, astronomers have been working to measure the universe's density with ever-increasing precision. They've counted galaxies, measured the cosmic microwave background radiation, tracked the motion of distant supernova, and studied the large-scale structure of cosmic matter. The results have been surprising and sometimes contradictory. Early measurements in the 20th century suggested that the universe might have less than the critical density, implying an open, infinite geometry. But these measurements were difficult and uncertain, and scientists knew they were missing significant components of cosmic matter and energy. The first major surprise came with the discovery of dark matter. In the 1970s and 1980s, astronomers realized that galaxies and galaxy clusters contained far more matter than they could see in stars and gas. This invisible dark matter outweighs ordinary matter by a factor of about 5 to 1. When dark matter was included in density calculations, the universe appeared to be much closer to the critical density. But the biggest surprise was yet to come. In 1998, two independent teams of astronomers studying distant supernovae made a shocking discovery. The expansion of the universe wasn't slowing down due to gravitational attraction, as everyone had expected. Instead, it was speeding up. This accelerating expansion implied the existence of a repulsive force pervading all of space, which physicists dubbed dark energy. Dark energy appears to make up about 68% of the total energy density of the universe, with dark matter contributing another 27%, leaving only 5% for the ordinary matter that makes up stars, planets, and people. When all these components are added together, the total density of the universe appears to be remarkably close to the critical density that would make space geometrically flat. The most precise measurements, based on observations of the cosmic microwave background by satellites like the Planck mission, suggest that the universe is flat to within less than 1% uncertainty. If these measurements are correct, then space is indeed infinite. The universe extends forever in all directions, containing infinite volume, infinite matter, and infinite energy. This is both a profound scientific conclusion and a mind-bending philosophical puzzle. But let's pause here and really think about what infinite space would mean. If space goes on forever, then everything that's physically possible must happen somewhere. In an infinite universe with finite matter density, the laws of probability guarantee that every possible arrangement of matter will occur infinitely many times. This leads to some truly bizarre implications. In an infinite universe, there must be infinitely many regions identical to our observable universe, down to the quantum level. there must be infinitely many planets exactly like Earth, with infinitely many people exactly like you, living lives identical to yours in every detail. But there must also be infinitely many versions of Earth where small differences have led to completely different histories. Think about this for a moment. If space is infinite, then somewhere out there, there's a planet where dinosaurs never went extinct, where you became a professional athlete instead of whatever you actually do, where you were born in a different century, or where you never existed at all. Every possible variation on your life story is playing out somewhere in the infinite expanse of space. This concept, known as the multiverse or many-worlds scenario, emerges naturally from the mathematics of infinite space. It's not science fiction or philosophical speculation. It's a direct consequence of well-established physical theories applied to an infinite universe. But the implications go even deeper. In an infinite universe, every finite region of space, no matter how large, must contain only a finite number of possible arrangements of matter and energy. This means that patterns must repeat. The arrangement of matter in our observable universe, with all its galaxies, stars, and planets, must occur again and again throughout infinite space. The physicist Max Tegmark has calculated that in an infinite universe, you should expect to find an exact duplicate of yourself within a distance of about 10 to the power of 10 to the power of 28 meters. That's a 1 followed by 10 billion 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 zeros. This distance is incomprehensibly vast, but in an infinite universe, it's just a finite journey. These ideas might seem like pure theoretical speculation, but they're grounded in solid physics and mathematics. The question isn't whether these duplicates exist if space is infinite. The laws of probability guarantee that they must. The question is whether space actually is infinite and whether these mathematical certainties apply to physical reality. This brings us to one of the deepest philosophical questions about infinity. Can the physical universe actually contain infinite quantities? This question has puzzled scientists and philosophers for centuries, and it remains unresolved today. Some scientists argue that physical infinity is impossible. They point out that all of our measurements and observations are finite, and that infinity often leads to mathematical paradoxes when applied to physical systems. In quantum field theory, for example, calculations often yield infinite results that must be renormalized to make physical sense. Perhaps these infinities are signs that our theories break down at some fundamental level. Other scientists embrace physical infinity as a natural consequence of our best theories. General relativity and quantum mechanics don't contain any built-in limits on the size or extent of the universe. If these theories are correct, and if our measurements of cosmic geometry are accurate, then infinite space is simply a fact about reality that we must accept, however counterintuitive it might seem. This debate touches on fundamental questions about the relationship between mathematics and physics. Mathematics can handle infinite sets with precise rules and operations, but does that mean physical reality can actually contain infinite quantities? Or are there limits to what mathematics can tell us about the real world? The question becomes even more complex when we consider the quantum nature of reality. According to quantum mechanics, the universe is fundamentally discrete at the smallest scales. Space and time themselves might be made up of indivisible units, like pixels in a cosmic computer screen. If this is true, then true infinity might be impossible, even in an arbitrarily large universe. String theory, one of the leading candidates for a unified theory of physics, suggests that space might have additional dimensions beyond the three we experience directly. These extra dimensions might be finite in size, even if the three dimensions we observe extend infinitely. This would create a strange hybrid, a universe that's infinite in some directions but finite in others. Loop quantum gravity, another approach to unifying general relativity and quantum mechanics, suggests that space itself is made up of discrete units at the Planck scale, about 10 to the negative 35th power meters. In this view, space is like a cosmic fabric woven from individual threads. This discreteness might prevent true infinity, even if the number of discrete units is arbitrarily large. But even if space is discrete at the quantum level, it might still be infinite in the sense that it contains infinitely many discrete units. The question of whether infinity exists in nature remains open, and it might depend on aspects of physics that we don't yet understand. Let's step back from these deep theoretical questions and consider what we can actually observe about cosmic space. While we can't directly measure whether the universe is infinite, we can look for clues in the cosmic microwave background, the afterglow of the Big Bang that fills all of space. The cosmic microwave background provides us with a snapshot of the universe when it was only 380,000 years old, the moment when it became transparent to light for the first time. This radiation carries information about the geometry and contents of the universe encoded in tiny temperature variations across the sky. If the universe were finite and relatively small, we might expect to see repeating patterns in the cosmic microwave background, like echoes of the same structures appearing in multiple directions. Scientists have looked carefully for such patterns, but they haven't found any convincing evidence for them. This doesn't prove that the universe is infinite, but it suggests that if it's finite, it must be much larger than our observable universe. Another way to probe the infinity question is to study the large-scale structure of the universe. If space is infinite, then the distribution of matter should look roughly the same in all directions when averaged over sufficiently large scales. This property, called statistical isotropy, is indeed observed in galaxy surveys and cosmic microwave background maps. The universe appears to be homogeneous and isotropic on the largest scales, consistent with the idea that it extends infinitely in all directions. But this observation is also consistent with a finite universe that's much larger than our observable horizon. The search for evidence of finite or infinite space has led to some creative observational strategies. Some astronomers have looked for cosmic circles in the cosmic microwave background, patterns that would appear if light from the early universe had traveled all the way around a finite cosmos. Others have searched for correlations between widely separated regions that might indicate the universe is smaller than it appears. So far, these searches haven't turned up convincing evidence for a finite universe, but they also haven't definitively proven that space is infinite. The observable universe provides only a limited window into cosmic geometry, and the full extent of space might remain forever beyond our direct observation. This limitation brings us to a fundamental epistemological question. Can science answer questions about infinity? Science is based on observation and measurement, but infinity by definition extends beyond any finite observation. If the universe is infinite, can we ever know it for certain? Or are we limited to making educated guesses based on finite data? Some philosophers of science argue that questions about infinity are inherently unscientific because they can't be definitively answered through observation. Others contend that science can make probabilistic statements about infinity based on theoretical frameworks and limited observations, even if absolute certainty is impossible. This debate reflects a deeper tension between theoretical physics and empirical science. Modern cosmology increasingly relies on mathematical theories that make predictions about unobservable regions of space and time. The multiverse, extra dimensions, and cosmic inflation all involve physics beyond the reach of direct observation. How do we decide which of these theoretical constructs correspond to physical reality? The question of infinite space also intersects with one of the most active areas of modern cosmology, the study of cosmic inflation. In the early 1980s, physicist Alan Guth proposed that the universe underwent a period of exponential expansion during its first fraction of a second. This inflationary epoch would explain several puzzling features of the cosmic microwave background, including its remarkable uniformity across the sky. But inflation theory has profound implications for the infinity question. Most models of cosmic inflation suggest that the inflationary process continues in most regions of space, even after it ends in our local region. This leads to the concept of eternal inflation, where new universes are constantly being created through quantum fluctuations in the inflating spacetime. If eternal inflation is correct, then our observable universe is just one of infinitely many pocket universes embedded in an ever-expanding inflationary background. Each pocket universe might have different physical properties, different values for the fundamental constants, and different laws of physics. The total multiverse would be infinite, not just in space, but in the diversity of physical realities it contains. This inflationary multiverse adds yet another layer to the infinity paradox. Even if our local universe is finite, it might be embedded in an infinite ensemble of universes. The question of whether space is infinite becomes entangled with questions about the nature of physical law and the uniqueness of our cosmic environment. Some versions of string theory suggest that there might be up to 10 to the power of 500 different ways to construct a universe, each with different physical properties. If eternal inflation creates infinitely many universes, then every possible type of universe should be realized infinitely many times. This would make our particular universe, with its specific physical constants and laws, just one member of an infinite cosmic democracy. The implications of this inflationary multiverse are both exhilarating and troubling. On one hand, it suggests that existence is incredibly rich and diverse, with infinitely many realities exploring every possible way that physics could work. On the other hand, it raises difficult questions about the nature of scientific explanation and prediction. If every possible universe exists somewhere in the multiverse, then any observation we make is consistent with the theory, because there must be universes where that observation is realized. This makes the multiverse hypothesis difficult to test or falsify, leading some critics to argue that it's not really science at all. The debate over the multiverse reflects broader tensions in modern theoretical physics. As our theories become more mathematically sophisticated and make predictions about unobservable realms, the line between physics and metaphysics becomes increasingly blurred. The question of whether space is infinite sits right at this boundary between what we can know and what we can only theorize about. But perhaps the most profound aspect of the infinity question isn't scientific at all, but existential. What does it mean for human life and consciousness to exist in an infinite universe? How should we think about our place in reality if space extends forever in all directions? The idea of infinite space can be deeply unsettling. It suggests that we are infinitesimally small parts of an incomprehensibly vast cosmos. Every human achievement, every moment of joy or sorrow, every work of art or act of love is dwarfed by the sheer scale of infinite space. In the face of such immensity, human life can seem vanishingly insignificant. But infinity can also be liberating and inspiring. If space is infinite, then the possibilities for existence are truly limitless. Somewhere in the vast expanse, every dream is realized, every story unfolds, every potential is actualized. The universe becomes not just vast, but infinitely creative and diverse. The physicist Brian Greene has written about the existential vertigo that comes from contemplating cosmic infinity. The idea that there might be infinitely many copies of ourselves living infinitely many variations of our lives challenges our most basic intuitions about identity and uniqueness. Are we individuals, or are we patterns that repeat throughout infinite space? Some philosophers have argued that infinity actually enhances rather than diminishes human significance. In an infinite universe, every action matters because it contributes to the infinite diversity of experience. Every choice creates a unique path through the space of possibilities, adding something new to the cosmic story. The mathematician and philosopher William James suggested that infinity gives ultimate meaning to finite existence. If the universe were finite, then eventually everything would end and all human achievements would be forgotten. But in an infinite universe, every moment of consciousness, every act of creativity, every experience of beauty or love becomes an eternal part of reality. These philosophical reflections bring us to one of the most ancient and persistent questions in human thought. What is our relationship to the cosmos? Are we separate from the universe, or are we part of it? Do we observe reality from the outside, or are we embedded within it? The question of infinite space forces us to confront the boundaries of human understanding. We are finite beings trying to comprehend infinity, limited minds attempting to grasp unlimited reality. This tension has driven human inquiry for millennia, from ancient philosophers to modern cosmologists. Perhaps the most honest response to cosmic infinity is a kind of humble awe. We can study its mathematical properties, search for observational evidence, and construct theoretical models, but we may never fully grasp what it means for reality to extend without end. The infinity of space might forever remain partially mysterious, a reminder of the limits of human knowledge and the boundless nature of existence. But this mystery is also part of what makes the question so compelling. In an age where scientific knowledge seems to advance exponentially, the possibility of infinite space reminds us that there are still fundamental questions about reality that remain open. The universe continues to surprise us, to challenge our preconceptions, and to reveal new depths of complexity and beauty. As we continue to probe the cosmos with increasingly sophisticated instruments and theories, we may eventually find definitive evidence for or against infinite space. Future observations of the cosmic microwave background, searches for repeating patterns in cosmic structure, and advances in theoretical physics might finally resolve the infinity paradox. But regardless of what we discover, the question of infinite space has already transformed our understanding of reality. It has forced us to confront the relationship between mathematics and physics, between theory and observation, between human experience and cosmic truth. It has revealed the profound strangeness of existence and the remarkable capacity of human minds to grapple with concepts that stretch far beyond everyday experience. The journey through infinite space is also a journey through the history of human thought, from ancient philosophers wondering about the edge of the world to modern cosmologists mapping the structure of space-time. It connects us to a tradition of inquiry that spans cultures and centuries, a shared human quest to understand our place in the cosmos. In the end, the question of whether space is infinite might be less important than the fact that we can ask the question at all. The ability to contemplate infinity, to push beyond the boundaries of direct experience and imagine realities that extend forever in all directions, might be one of the most remarkable features of human consciousness. We are creatures capable of conceiving of infinity while remaining forever finite ourselves. We can imagine endless space while being confined to a single planet. We can contemplate eternal time while living brief lives. This capacity for transcendence, for reaching beyond our limitations through thought and imagination, might be what makes us truly human. So the next time you find yourself under a starry sky, remember that you're looking into a mystery that has captivated humanity for thousands of years. Whether those stars extend infinitely into space, or whether they're contained within some vast but finite cosmos, remains one of the great open questions in science. But either way, you're part of something remarkable, a universe capable of producing beings who can wonder about its own nature. The stars above you might be beacons in an infinite sea of space, marking locations in a cosmos that goes on forever, or they might be distant lights in a vast but bounded universe, their photons carrying information across billions of years to reach your eyes. In either case, you're witnessing something extraordinary, the ability of matter and energy to organize themselves in such a way that part of the universe can observe and contemplate the rest. This is perhaps the deepest paradox of all, not just that space might be infinite, but that finite beings like ourselves can grasp the concept of infinity at all. We are the universe's way of knowing itself, temporary arrangements of atoms and energy that have somehow acquired the ability to ponder the nature of existence. In contemplating infinite space, we're not just asking a scientific question about cosmic geometry. We're engaging in one of the most profound activities possible, finite beings reaching toward infinite understanding, temporary creatures grappling with eternal questions, small parts of the cosmos trying to comprehend the whole. Whether space is infinite or finite, whether our theories are right or wrong, whether we ever find definitive answers to these cosmic questions, the mere fact that we can ask them is perhaps the most remarkable thing of all. In a universe that might extend forever in all directions, filled with infinite possibilities and unlimited potential, we are the part that wonders, that questions, that seeks to understand. And in that seeking, in that eternal human quest to push beyond the boundaries of the known and venture into the infinite unknown, we find perhaps the truest expression of what it means to be human. We are finite beings blessed with infinite curiosity, temporary arrangements of matter gifted with the ability to contemplate eternity, small sparks of consciousness burning brightly in the vast darkness of space. The question of infinite space may never be fully answered, but in asking it, we reveal something infinite within ourselves, the boundless human capacity for wonder, for inquiry, and for reaching toward truths that lie forever beyond our grasp. In contemplating the possibility that space has no end, we discover that human curiosity, like space itself, might truly be infinite. This is the ultimate paradox of infinite space, not just that the universe might go on forever, but that finite beings like ourselves can conceive of forever at all. In grappling with infinity, we transcend our limitations and touch something eternal, and in that touch, however brief and however incomplete our understanding might be, we participate in the infinite creativity of a cosmos that has produced beings capable of contemplating their own existence. The stars continue to shine in the infinite night, and we continue to wonder about their nature and extent. In that wondering, we find our place in the cosmos, not as insignificant specks in an indifferent universe, but as the means by which the universe comes to know and understand itself. Whether space is infinite or finite, we are the part of reality that asks the question, and in asking, we make the universe a little more conscious, a little more aware, a little more alive. So when you look up at the night sky and wonder about the nature of space and time, remember that you're participating in one of the most ancient and noble human traditions. You're joining a conversation that began with the first humans who looked up at the stars and wondered where it all ends, and that continues today with scientists using the most advanced instruments ever built to probe the deepest mysteries of existence. The question of infinite space connects us across time and culture, uniting ancient philosophers and modern cosmologists in a shared quest to understand the nature of reality. It reminds us that despite all our technological advances and scientific discoveries, the universe still holds mysteries that can humble and inspire us. And it suggests that the greatest adventure of all might not be traveling through infinite space, but using our finite minds to contemplate the infinite possibilities that surround us every moment of our lives. In the end, whether space is infinite or finite, bounded or boundless, our response to the mystery should be the same: wonder, curiosity, and gratitude for being part of a universe remarkable enough to produce beings capable of asking such profound questions. We are the cosmos thinking about itself, finite expressions of infinite possibility, temporary manifestations of eternal mystery. And in that mystery, in that endless questioning, in that eternal reaching toward understanding, we find not just the nature of space, but the nature of ourselves. We are beings capable of infinity, creatures who can touch the eternal through thought, finite sparks of consciousness illuminating the infinite darkness of the unknown. In contemplating endless space, we discover that human consciousness itself might be the most infinite thing of all.